and most of you who are connected know that much better than I know, that what insurers are fearing most anxiously is the accumulation of risk, the accumulation of one risk with other dangerous risk, as far as this accumulation is for long the main source of most catastrophic risk. One of the current pressing questions concerned the consequence of global warming and climate change on mortality. Economists have for long looked to this question with relatively reassuring conclusions. It is not a higher temperature that is by itself a significant risk, but the change of temperature, especially when confronted with shock waves. But economists have mostly looked at the average consequences, but not in detail, and their analysis has been rather general, focused geographically. And therefore, now it's time to have more encompassing studies. Therefore, the need for more in-depth studies on the subject. It is what Associate Professor Hanley and Anastasios Panagiotelis have done in the project Who, When and Where, Assessing Mortality Risk of Climate Change. It's a project supported by the SCOR Foundation for Science. I am therefore pleased to introduce Professors Hanley and Professor Anastasios Panagiotelis, who will moderate the present online webinar organized by the SCOR Foundation for Science with the title, of course, Assessing Mortality Risk of Climate Change. Professors Hanley and Anastasios Panagiotelis will present us the latest research results of the project. I would like to underline that this project is a pioneering one that quantify the mortality risk associated with climate change for insurance risk management. Its approach can also be used to assess the impact of climate change on morbidity based on prevalence and/or incidence rate. Its modeling framework will be applicable to mortality and morbidity experience of an insured population to better understand the impact of climate on insurance portfolio. Professor Hanley is an associate professor at the Center of Actuarial Study, Department of Economics from the University of Melbourne. She is leading the project. Professor Hanley already visited SCOR head office in Paris and presented her research on climate-driven mortality during a workshop on July 12, 2023, shedding light on the assessment and the quantification of the adverse impact of climate change on population mortality experience. Professor Anastasios Panagiotelis is an associate professor of business analytics at the University of Sydney Business School and director of the International Institute of Forecasters. Professor Hanley, Professor Anastasios Panagiotelis, you have the floor for 30 to 60 minutes, as is your choice, as you want. Please, for those participating to this webinar, notice that questions will be asked after the presentation, except if it is a question of misunderstanding or non-understanding for any technical reason. Of course, as usual, the webinar will be closed at 3:30 p.m. Paris time, that is, in a little less than 1.5 hours. Please, you have the floor.
Thank you so much, Philip, for the very nice introduction. And I may just share my slides because I'm going first with the presentation.
Yes.
Yep. Can everyone see the slides?
Yes, I see that.
Yep. Okay, cool. Thank you. So, hello everyone. My name is Han, and I'm an associate professor from the University of Melbourne. It's a pleasure for me today to present our latest research on climate-associated mortality risk. I'll be presenting together with my research collaborator on this project, Anastasios Panagitelis from the University of Sydney. First, we would like to thank the SCOR Foundation for Science for funding our research project, When, Who, When, and Where, assessing mortality risk of climate change. In particular, we would like to thank Philip, Zeying, and Adam for their constant help and support throughout this project. And this is a joint work with Anastasios, as well as Professor Rob J. Heitman from Monash University in Melbourne. Our presentation today will be based on the results of this research project. So here comes the outline of our presentation. I will be covering background and motivation of this project, as well as data collection, processing, and visualization. Anastasios will then talk about the modeling framework and the empirical results of our project. So we will start with background and motivation. As the title implies, we are looking to assess mortality risk of climate change. And indeed, the link between climate change and human mortality has been long established. Well, there's no cause of death called climate change. Environmental factors have always been playing an important role on population health and mortality. According to the WHO, between 2030 and 2050, climate change is expected to cause approximately 250,000 additional deaths per year. And the WHO identified three main channels for the impact, namely weather-related catastrophes, extreme temperatures, and climate-sensitive infectious diseases. And in this project, we will focus on the second channel, which is extreme temperatures. And this is because there are more available data on temperature, and it is easier to quantify the impact. So from a research perspective, we actually already know a lot about how extreme temperatures affect mortality. So this is research not only in actuarial science, but more so in environmental science and climate science. For example, a recent study found that globally, approximately 5 million deaths were associated with non-optimal temperatures per year. And that is 1 out of 10 deaths in the world during 2000 to 2019. And the research has also found that extreme heat associated excess mortality is more immediate, whereas the increase in mortality following extreme cold is longer lasting. It can last for a couple of weeks. And finally, we also know that the elderly are more fragile to extreme temperatures, so both extreme heat and extreme cold. And different regions will react to extreme temperatures differently. So these are all based on existing research, and we already know quite a lot about the relationship between temperature and mortality. So building on these results, what do we contribute? And what research question are we answering? On the next slide, I summarize the three main research questions as follows. So the first research question is, who are the excess deaths? In this project, we try to identify the age groups particularly sensitive to climate change. And the second question is, when do excess deaths occur? We want to determine if more excess deaths or excess mortality occur in winter or in summer months? And lastly, where are the excess deaths? We try to identify regions that are most vulnerable to climate change, because climate is a very localized concept. So the climate risk of mortality is not uniform across different regions. And we want to have a framework able to identify and quantify these different impacts. So before we go into the project of extreme temperature versus mortality, let's now take a step back and review the shape of mortality surface. In our project, we use the US data on temperature and mortality as our empirical studies. So throughout this presentation, all of our illustrations will be based on the US data. So as I've mentioned before we're talking about temperature data, let's take a step back and review some of the trends and patterns. And I think a lot of you guys will already know very well about these features of mortality. And why are we doing this? And this is because temperature is not the only contributor to changes in mortality. So when we assess the impact of temperature on mortality, we need to control for these known patterns and trends in the mortality surface. So in figure 1 on this slide, I'm showing the national level male mortality for the US from 1969 to 2019. And from this plot, we can see that across all age groups, there has been a decrease in mortality or mortality improvement over time. And we can also see the very well established high infant mortality pattern, as well as the accident hump around age 20. So this is the mortality pattern across time and age. As I've mentioned before, there are regional differences in mortality experience and how they react to extreme temperatures. If we take snapshots of state-level US mortality, so in this second figure, we plot male mortality rates across the US, so taking two snapshots, 1999 and 2019. So 2019 on the right, 1999 on the left. We can see that for the three selected age groups, there are regional patterns. There are geographical differences in mortality experience. So it's quite clear that in some of the southern states, the mortality rates are higher especially comparing to the East Coast and the West Coast. So it means that there are disparities in mortality experience across different regional areas. And when quantifying the impact of temperature on mortality, we need to take these differences into account as well. So after we review the patterns in mortality across time, across age, and across spatial dimensions, let's look at some of the existing research on temperature and mortality. I won't be going into details of these existing studies. And the purpose of showing you or talking about some of the study is to draw your attention on the geographical resolutions that have been used in this research. So the first research I'm going to mention is actually one of my own. So in this project, me and my collaborator, we look into the dependence in joint extremes in temperature and mortality. And the geographical resolution that we used is basically shown in this map. So we're using data from 6 continental US regions. So these 6 continental regions, as you can see, they combine a couple of states in each of the region. And you can imagine that like within each of the continental region, the climate would not be uniform, would not be exactly the same. Sometimes they can vary quite a lot. For example, the SPL region. So the reason why we use continental level as the geographical resolution is because it's simply a limitation of the data we have on temperature data. So this is a research done obviously in the perspective of actuarial study or actuarial research. On the other hand, if we review some of the literature in environmental science or climate science, we can see that they have been using data at much finer geographical resolution. For example, this very well-known study studying the relationship between temperature and mortality. So in this paper, they actually use temperature and mortality data from New York. So this is not the state of New York. This is actually the city of New York. So you can see I have a map of New York City here. You can see that it's very fine geographical resolution. Okay, and as you can imagine, obviously, this is good because we have very fine geographical resolution in such studies. But the downside is because it's a little bit too fine, the sample size becomes a problem, could be a problem, and sometimes we just don't have good quality data because it's too small a sample size. So as you can imagine, when we decide what will be our geographical resolution for this project, there is a trade-off between like how fine the geographical area is such that within this geographical resolution, the climate is kind of similar or uniform versus how good the data is, the quality of the data is based on the sample size. So we don't want to have regions that are too small, so the quality of data is poor. On the other hand, we also don't want to have two regions that are too big, so the climate varies a lot within each region. And more importantly, I forgot to mention just now, we want to conduct an analysis that contains the entire US, not just one city, not just one state. We want to have a study that utilizes the data across the US. So in our data, or in our project, what did we choose? We've chosen this geographical resolution called the climate divisions. So the concept of climate division is proposed by NOAA and is actually also defined by NOAA. So it's defined in the concept of climate science. So within each of these climate divisions, they have a similar climate. So that's how they came up with these 344 climate divisions within the US. And here I plot. I have the plot of average temperature in the US across the 344 climate divisions. And you can see the data is based on the latest data in February 2024. So the northern states or the northern regions are cooler comparing to the southern regions. They are hotter. Okay, and for more information on these climate divisions, you can visit the NOAA website. So once we have decided which geographical resolution we're going to use, we can now talk about our data collection, processing, as well as I can show you finalize the data. I can visualize the data with you guys and to show you how the data look like. In terms of the death data, we use US county level monthly death data for the period of 1968 and 2018. And we obtain the data from two sources. The first one is NCHS, and the second one is CDC Wonder. So I need to make two important notes here. So because there's no publicly available data on monthly population exposure, particularly at the county level, in this project, we simply assume that we have constant exposure throughout the year. So throughout the 12 months, we have constant exposure. And secondly, and the second one is also I think a lot of people already know, the CDC Wonder online database is a very good database, but a downside of this database is it censors death counts between 0 and 9 due to privacy constraints for years 1989 onwards. So if in a particular month for a particular age group, the observed number of deaths is less than 10, then in the data, it will simply be surprised, and we wouldn't know how many deaths happened in that month for that age group. So in the modeling exercise, in the modeling framework, Anastasios is actually going to talk about how we deal with this data suppression issue in more detail. So that's the death data, county level, monthly frequency. And here I simply show you a map of US counties, and you can see it's super fine geographical resolution, and there are more than 3,100 counties in the US. So on the other hand, with the temperature data, we collect the corresponding monthly temperature data at climate division level. And this is already the finest level we can have for temperature data in the US. And we collect such data from NOAA. And I also make two important notes here. First one is there are 344 climate divisions. So in terms of the resolution, obviously, climate divisions are larger than counties, but much smaller than states. There are 50 states in the US. And secondly, the second point is actually very important. The borders of climate divisions. So how the climate divisions are defined. So these are the borders of climate divisions. So these overlap with those of counties. So in certain cases, the borders of climate divisions actually overlap those of the counties. So we need to take some care when combine the death count data together with the temperature data. So we need to be very, very careful mapping the data from county level to climate division level, because the mapping may not be one-to-one. If we just do exact matching, then we may be counting the number of deaths for certain counties twice. So I quickly show you, this is the map of US climate divisions. The question of processing the data, a large part of it, a key part of it is how do we match counties or map counties into climate divisions. So in this simple illustration, I gave you some examples. So from this plot, we have the pink line showing the borders of climate divisions. So there are 3 climate divisions in this plot. So the first one, the second one, and the third one. So 3 climate divisions on this plot. And the gray lines represent the county borders. So these are the gray lines, and they represent the county borders. And finally, the blue dots represent the county population center. This is not the geographical center of a county, but where the center of the population is. So we use county population center to determine the mapping rule. So for example, if we look at this one, this blue dot, so this blue dot represents the population center of this county. Okay, so the county I'm outlining here. And because the blue dot falls in the first climate division, so climate division 1, so we map the number of deaths from this county to climate division 1. Another example here, the blue dot of this county. So this county, worth noting that this county actually overlaps all 3 climate divisions. So how do we map the number of deaths from this county to a certain, only a unique climate division? And here, because the center of the population for this county falls in climate division number 3. So this is 1, 2, and 3. So we map the number of deaths or the death data of this county to climate division 3. And similarly, for this blue dot or this county here, we're mapping the number of deaths into climate division number 3. Okay, so that's just a simple illustration of how the mapping works. Once we apply this mapping rule for the entire US, let me now show you, take a quick glance at the data. So we have, in the figure, we have the plot of log mortality for ages 75 to 84, and this is based on January 2018 data. Okay, so we can see that the darker the color is, the higher the mortality is. And this is based on climate division level, okay, 344 climate division level, and we're plotting the log mortality for each of them. And we can see that the observation is consistent with the previous research. The southern states, the southern states or the climate division in southern states have higher mortality comparing to the rest of the US. And another thing I want to point out is these gray areas, because I've talked about data suppression issue before, and these gray areas are basically representing that we don't have information for that month. For that month, we only know the number of deaths in that month for this age group is less than 10, but we don't know exactly the exact number of deaths for these climate divisions in January 2018 for age group 75 to 84. So that's just a snapshot, a quick glance at the data. Obviously, we have the data for different months throughout time, as well as for different age groups. So before I move on to, I hand over to Anastasios for the modeling framework, I will end my part of the presentation with the challenges that we face in quantifying mortality risk due to extreme temperatures. So first of all, the relationship is nonlinear. For example, temperatures may impact mortality only when above or below certain thresholds. So we know that at the 2 extreme ends of the spectrum, we really see the impact of extreme temperature. Otherwise, the impact may not be that big. And second, this nonlinear relationship may also vary with geography, as shown in many of the previous plots, because climate, temperature, these concepts are all very localized. So different regions will have a different regions have different mortality experience, and on top of that, they also have a different climate or different temperature behaviors. So, for example, regions with widespread usage of air conditioning should be better adapted to heat waves comparing to other regions. So it's not only geographic, it's not only a climate thing, it's also a social economic thing. So more wealthy area may be better adapted to climate change or to extreme temperatures. And we want to take this into account. And finally, there is a need to control for time trend and age patterns that can confound the relationship, because we know, especially for older age groups, it's natural to have higher number of deaths in winter versus summer, but it's not really related to what we're trying to quantify, which is the extreme mortality risk associated with climate change. So we want to separate or disentangle the normal trend and the seasonal patterns in the data versus, like this temperature extreme, these extremes in mortality or additional deaths due to extreme temperatures, extreme temperatures. So in our modeling framework, like these challenges will be addressed. And that's the end of my part of the presentation. I will now hand over to Tas for the modeling framework and the empirical results. So I think I may stop sharing.
I might ask you to stop sharing, otherwise I'll have to ask you to change slides every few minutes.
Yeah.
So I'll take over the sharing.
Yeah, I'll mute myself.
One moment, I'm just working this out in.
Yeah. Also, I hope there are no burning questions at the moment. If there are, I will be monitoring the chat.
Okay.
Yeah.
So you can see my slides now, is that correct?
Yeah.
Yes.
Okay.
Yes. Thanks.
So I'll discuss the statistical model that we use. Now, I'm aware of the fact that in such a large audience, I may be speaking to people with varying levels of statistical expertise. So what I'll aim to do is just give the logic of the model that we use. Also, what we will be looking at is just a snapshot of the full results. So really the aim here is just to give you a sense of what we've done in this research. So the model that we are looking at essentially boils down to a regression model, although one that has to account for the complexity of the data that we look at. So we have a dependent variable here in blue, YIXT, and this is our annualized log mortality for climate division I at time t for age group X. So keep track of those subscripts. I refers to the climate division or region, T to time, and X refers to an age group. And the mean is going to vary across those different factors. And the second equation here shows how that happens. So our mean is given by a global factor, alpha. And then we have a set of gammas here, which are our random effects. So depending on the superscript in parentheses, that informs you of the factor that the random effect corresponds to. So gamma ICD refers to a regional random effect or a climate division random effect. Gamma year refers to a random effect for each year, since there are trends over time in mortality. Gamma month refers to the monthly pattern, so the seasonality within a year. Gamma X age refers to different age groups. Obviously, mortality will vary across different age groups. We also have an example here in gamma year age of a two-way effect. So the trends over time, the improvements in mortality rates over time are not the same for all age groups, and we'll actually see that in our results. And all of these gammas here act as controls because we know that temperature is not the only thing that influences mortality. So when we look at the effect of temperature, we need to control for as many of these factors as we can. Of course, once we've done the controls, we need to look at temperature. And in this specification that I'm showing here, our temperature is a function, some nonlinear function. That's the effect of temperature on mortality. And it's indexed by I. In other words, the effect of temperature on mortality is going to be different for each climate division. And then temperature here is the temperature within a climate division for a particular month. So that's this specification. There are various specifications that we can use, but they're all based on a similar logic. Random effects that control for some of these confounders of the mortality experience, and then a nice nonlinear function here to account for the effect of temperature on mortality. Now, we have to keep in mind that the issue of suppression, and that's an issue that we explicitly take care of in this model. So when we compute log mortality, that is basically deaths divided by exposure or population, to account for the fact that months have a different number of days and even years have a different number of days, since there are some leap years in our sample. We just have to correct this and get annualized mortality rates. But of course, we know that we don't observe these mortality rates for every single combination of climate division, age, and temperature. And that's because in some of the more sparsely populated climate divisions, there may be fewer than 10 deaths within a given month. And in this case, the observation is suppressed. However, even in that case, even if we observe a suppressed observation, we do know the upper bound on YIXT, on the log mortality rate, because we know that if there were no more than 10 deaths, then this expression at the bottom tells us the upper bound of deaths for that particular combination of age, month, and climate division. So we either observe a Y directly, or we observe some upper bound for that. Now, when it comes to looking at this in our model, the approach that we're going to take is a Bayesian one, because the Bayesian approach has a very natural way of dealing with this suppressed data. And the way we do it is to think of our model rather than in terms of Y, which is what we observe. We think of it in terms of Y star. We can think of Y star as a latent variable. It is what log mortality either is observed as or would be if we were able to observe it. So you can see here when we look at the definition of Y star, if the data is not suppressed, then it's just YIXT, exactly what we observe. Otherwise, we can put a prior on this Y star, and the prior that we put on is that it follows the distribution with the mean given from the likelihood equation, but this is truncated so that the Y star is less than that upper bound that we calculated on the previous slide. So if the data is suppressed, we don't observe Y star, we just know that it's below this value of U, and we know the distribution of that from the likelihood. Now, one of the advantages of the Bayesian approach is that we can treat these latent variables, these Y stars for the suppressed data, like any other parameters in our model, and that means that we can estimate them. So as well as handling the issue of data suppression by taking a Bayesian approach, we're also able to actually infer what those mortality rates would have been, and that gives us a way of imputing all of the missing data, which could be of use in follow-up studies. Now, the other purpose of taking a Bayesian approach is to use priors. And something that I should note if we go back to the original model is that this is an extremely highly parameterized model. So there's a feeling here that we're looking at an example of big data because there is a lot of data here, but with big data comes a lot of parameters. And when you have such a highly parameterized model, your big data problem starts to resemble a small data problem. For instance, here there would be, as we noted before, 300 separate random effects for the climate divisions, 20 effects for the year, 12 for the month. This year age surface has 80 separate parameters, and then we're going to somehow do this temperature effect non-linearly. So there's a lot of parameters in this model. And where you have a lot of parameters in the model, it makes sense to borrow strength. And the thing is, in this data, there is a lot of structure, and there's a lot of structure in the sense that we can talk about neighborhoods of these parameters. What do I mean by neighborhoods? Well, if we think about the climate divisions, we have climate divisions that are next to one another. And we would expect random effects or regression effects corresponding to neighboring regions to be quite similar. So we can take that a priori assumption and build that into our model so that we can estimate such a finely detailed model. But this idea of neighborhood doesn't only extend to different regions, it also extends to different years. For example, 2005 and 2006 are neighboring years. Also to neighboring months, March and April are neighboring months, and also to neighboring age groups. The age groups that we look at here are in 10-year bands, but obviously the 55 to 64-year-old age group will be more similar to the 64 to 75-year-old age group. So the way that we shrink these neighboring random effects or these neighboring regression effects together is using something known as an intrinsic conditional autoregressive prior. It dates back to Bisag and Kuperberg. And there's several ways which we can come to understand this, but I think, again, I just want to provide some intuition, and that's best provided by thinking about these neighborhoods using graphs. Now, what do I mean by graphs? Well, a graph is just an abstract mathematical object that has some sort of nodes and it has some sort of edges. Now, in our case, for this particular model, the nodes are going to correspond to those random effect parameters, those gammas in the model. And then the idea is that an edge connects two nodes, and in our case, the edges are going to correspond to differences between random effects, and in particular between neighboring random effects, using this concept of neighborhood that I mentioned before. And then this ICAR prior just boils down to something quite simple. It's just a normal prior with a mean of 0 on those differences between neighboring random effects. Now, the idea behind this, and I think the intuition of this should be quite clear, even if the details are not, and that is that you are taking the differences between these neighbors and you're shrinking them to 0. That has the effect of shrinking random effects for neighboring regions or neighboring age groups closer to one another. So that's the basic idea behind what we do in this model, and that's what allows us to estimate a model with so many parameters. Okay, so just to make this concept of neighborhood a little bit more concrete and how it connects to graphs, here we've got an example well, these are not climate divisions, these are states. Climate divisions are quite small, so I thought this would be better illustrated using states. And what we can see here is, I've just picked 5 states here in the south or the middle of the US. And we can see that Colorado is neighboring New Mexico and Oklahoma. So the random effect for Colorado would be joined to New Mexico and to Oklahoma. But Colorado does not have a border with Texas, so there would be no edge between Colorado and Texas. And then what we would do if this was our spatial resolution, we would be shrinking the random effect for Colorado to be closer to that of New Mexico and Oklahoma. Now I repeat, we do not do this at a state level in our analysis. We do this at a climate division level. This is just to illustrate things. Similarly, we can look at the age graph. So the graph for ages is that we just take the adjacent ages and it is in a chain. So again, we're going to shrink the 55 to 64 age years to the 65 to 74-year-old age group. So this is the kind of graph we get for ages. For year effects, we get a similar graph. For the month graph, it's the same type of idea. Neighboring months are connected to one another. Of course, the year is a cycle. So January is connected to February, but it's also connected to December, since January comes between December and February. And although I've said this so far for the one-way effects, we can also do this for the two-way effects. And to do that, the way we do that is by constructing what is known as the Cartesian product of two graphs. To illustrate that, I'll just mention the age-year effect, which is in our model. So the nodes of this graph will become pairs of ages and years. For example, 2005 and the age group 55 to 64. and then we put an edge between those nodes if the year is the same and if the age are neighbors. So an example is given here, 2005, 55 to 64, and 2005, 65 to 74. And the same thing would happen if the years were neighbors and if the age were the same. So again, we're going to shrink the effects of these neighboring nodes closer together. To give you an idea of what that looks like in a picture with the graph, this is the way we do shrinkage. So anywhere where you see an edge, we're shrinking the random effects of those two together. Okay, I'll now quickly talk about the way that we handle the nonlinear regression. And to be brief, the way that we handle this is to take what is a nonlinear regression and turn it into a linear regression using something called B-splines. So the basic idea is that our function of temperature will be a linear combination of these B-splines denoted with capital BJ. So these are known functions. These can all be pre-computed. And then the only thing left to estimate are these beta j's. And what this does is gives us a lot of flexibility in the way that we can model the temperature effect. So again, just briefly to show you what the B-spline basis looks like, we have these known functions denoted with capital B. Each of them lives on a separate part of the support of the temperature. So the first one corresponds to lower temperatures. The seventh one in this picture corresponds to higher temperatures. And then these are combined with coefficients in a way that we can get a very flexible range of functions. So just to, I've got on the next few slides a few illustrations of that. So different values of beta. For this set of values of beta, we get a downward trending line. For this set of values of beta, we get a U shape, which is closer to the shape we would expect for temperature effects. But on the other hand, we must be careful because there are also some values of beta that will give us a function that is very wiggly, and this has the potential to overfit the data. So we want to avoid that. And the way that we do avoid that is to choose a very large number of basis functions. And then again, we're just using the same types of priors that we were using before, but instead of penalizing differences between neighboring random effects, we're penalizing the coefficients that correspond to neighboring B-spline functions. So this is a well-established technique in the literature, going back to something to work by Illes and Marx in the 90s. But this is a way to handle a nonlinear effect in this type of model. Now, one of the reasons we chose the B-spline, and something that's quite novel in the research that we've done, is that because we have climate division specific temperature effects, that's a large number of non-parametric effects to estimate, but we also want to do some shrinkage between the regions for those. So as well as shrinking the B-spline coefficients for each climate division, we also shrink those across the climate divisions. And that's basically done in the same way as we do the two-way effects. Okay, so just to finally recap on everything, at the bottom of it all, the model boils down to something quite simple. We have these deltas, which are differences between parameters. They have a normal prior, which has a mean of 0. This has the effect of shrinking those differences to 0. The variance of that prior follows a half Cauchy distribution. This has been well established to work in the literature. And the other priors are standard non-informative choices of priors. For the inference of this model, I won't speak too much about the details other than to say we use the no U-turn sampler, which is implemented in the software package Stan. And this represents the state of the art in MCMC inference at this stage. Again, I won't go into details of this algorithm. Okay, so with that established, I'll now show some empirical results. Again, because there are a large number of climate divisions, I just want to focus on a brief part of the story using results for Texas and Louisiana. So you can see here Texas and Louisiana. I say a small part of the US, but as I'm sure many of you are aware, Texas is a very big place. I think you could fit France into Texas multiple times. So this still does give us quite a range of climates, even in this small part of the US. And what we see here are those climate division random effects, and already we can see some variation in those. For example, this very southern tip of Texas, shown here in yellow, tends to have a lower mortality rate, whereas if you contrast that with parts of northeastern Louisiana, which are quite poor areas of Louisiana, you can see that the mortality rates there are quite a bit higher. What we see here is the monthly effect. So we do see that there are more deaths in the winter period in December and January. That's not solely attributed to temperature effects, because temperature effects are also in the model. Some of this is also due to holiday effects, car accidents, factors such as that. And what we see here is that this, again, is a seasonal pattern. It loops back on itself. The effect for December is close to January, which is a consequence of the prior we used. We see the yearly effect here, and the basic story that we see is similar to what we saw in the raw data, which is a decline in mortality rates, although that has flattened out since 2010. If we actually break that down into the two-way effect, so this shows us the trends over the years for different age groups. And it's quite interesting to see here that although mortality rates have declined for the older age groups, from 65, 75 and 85 years plus, we observe something quite different for the 55 to 64-year age group. And what we see here is that although mortality rates are lower for this group than the older groups, the trend is quite different. It goes down up to about the year 2010, and then there's actually an increase in mortality for this group. Now, this has been a fairly well-documented phenomena in the United States in particular. Various explanations have been given for this. The so-called deaths of despair, related to people losing their job, drug addiction, the opioid epidemic. These kinds of issues have been quite prevalent, and they have affected middle-aged people, in particular middle-aged men, in certain parts of the US. So it's important to see that we're able to capture these effects in our model, and indeed we do that. So now I'll finally move on to this regression effect between temperature and log mortality, just to give an idea of what that looks like. And this is the effect here. So the temperature is given in degrees Fahrenheit. I might require some help from some of the Americans on the talk to convert those, since we also use Celsius in Australia, as I'm sure you do in France as well. But what we do see here is, well, an interesting effect on the left-hand side. So what we see is, as it gets colder, there's a small range of temperatures for which mortality actually improves. And this is from about 40 degrees Fahrenheit to about freezing temperature, 32 degrees Fahrenheit. And at this range of temperatures, a lot of people are staying at home, so there is less spread of infectious diseases, and you actually see a bit of an improvement in log mortality. Of course, that gets worse as the temperatures get colder. Once we get below freezing and into temperatures that are well below freezing, mortality starts to spike up again. So that explains what we see on the left-hand side. It's also worth noting that the left-hand side, the colder temperatures are higher than the right-hand side. Again, this is in line with what we would expect to see. There are more deaths due to colder temperatures rather than hot temperatures. Of course, that doesn't mean that global warming is a good thing, since we know that climate change is associated with extremes at both ends of the scale. And then if we look towards the right-hand side, so if we look towards warmer temperatures, we can see that starting from the high 80s, there starts to be a little bit of a kick up in the mortality rates. So these are the extra deaths that could be attributed to hotter weather, at least in the data that we looked at. But I want to conclude by breaking that up, because recall that in this model, we don't just have a single effect of temperature on mortality, but we're actually able to get this relationship for every single climate division. And there's a few interesting things to look at here. I've picked out 4 regions from what we looked at earlier. So there is Southern Texas and Lower Valley Texas, the green and orange lines respectively. And these 2 areas are quite close to one another. And you can actually see that the green and yellow line are quite close to one another. So the shrinkage in the Bayesian model is having its effect there. Also, these are areas that are, right down in the south of Texas. They typically have very hot weather. In fact, if you looked at the, if you recall the map of the climate divisions with the average temperatures, you could see the southern tip of Texas was a very hot area. Now we can contrast these 2 regions with what we see in the high plains of Texas. So the high plains of Texas is right up in the north of the state. It's, as you can see from the name, it's at a higher altitude, so they don't get as much hot weather in the high plains of Texas. And we can also see northeast Louisiana, which you'll recall I mentioned earlier is a area where there's a higher level of socioeconomic disadvantage. So one interesting thing to see in these results is the way that these functions start to increase at a lower temperature, at least on the high end of the scale, for the high plains and for northeast Louisiana. So whereas in the very southern part of Texas, we only start to see that increase in mortality with temperatures in the high 80s, you actually start to see that with temperatures in the lower 80s for the high plains and for northeast Louisiana. And we conjecture that in the case of the high plains, that might be a lack of resilience because it doesn't get as hot there as often. There may be less proliferation of air conditioning in that area. Similarly, in northeast Louisiana, although it is quite hot there, again, due to the low the degree of socioeconomic disadvantage in that region, it might be the case that there's less resilience to these heat waves. So these are all things to factor in when we look at climate change, the way that it won't affect all climate divisions the same. And what our model allows us to do is quantify how resilient the climate change is going to differ across different parts of the United States. So just to wrap up, because we are pretty much on time here. So what insights did we make into the following questions? So who are the excess deaths? Well, this one was clear from the outset that this would be elderly people, particularly the oldest old, although we're able to quantify the extent to which that is the case. When did the excess deaths occur? Again, something fairly clear a priori, but something we're able to quantify, and that is with extreme cold temperatures and extreme heat, with the cold temperatures having more of an effect on mortality. And then finally, where are the excess deaths? And this is what I highlighted a little bit more today. And that has actually quite a complex pattern. And we see that climate divisions do exhibit differing levels of resilience to high temperatures or to low temperatures. That is very likely related to the socioeconomic factors in those regions. But that's something that will have a lot of implications for both insurers and for policymakers. So here are the references, and I think it's now time to open things up for questions.
Thank you so much. Thank you, Hans. Thank you, Anastasios. It was very interesting with very clear results, of course, to take with always with the statistical cautiousness that we are accustomed to. I have seen that there are some questions, and I just perhaps we'll ask Corina. Corina has asked a question, but maybe because there has been a slight discussion during your presentation, maybe Corina, you could explain yourself your question if you agree.
Yes, thank you very much. I would be interested to know whether the climate change also has effects on the accessibility of clean water, obviously for emerging markets, but also like in developed markets.
So we just have to decide who will fill. I think I'll provide an answer
You
first,
can
and
go
then Han
first.
might elaborate on it.
Okay.
So I do. I mean, that would be the case, that you would have an effect on clean water. Now, that's not the kind of thing that our results will shed light on, at least as I've shown them now. But what I would say is that if you are able to get reliable data on the water quality across different geographical regions, then you could use this methodology to come to similar conclusions. But again, it would be dependent on the data that you would get. I would also expect to see similar types of stories with respect to the diversity of the socioeconomic status in the United States. So although we talk, you mentioned developing countries and developed countries, I think it's important to recognize the variation within even developed countries when it comes to dealing with these kind of issues.
Thank you.
Yeah, I may just add on one more thing about, like this clean, availability of clean water. So in terms of, the negative impact on population health and mortality, I absolutely agree. But on the other hand, I think the impact might be a bit harder to identify and quantify, like comparing to temperature, simply because there could be a lagged effect from lacking fresh water or clean water, and then to some health problem, and then to excess mortality, and the precise lack of that impact. I mean, at least from my perspective, I haven't read too much about how long the impact may kick in after such a shortage of clean water. So that's in a sense that's a harder question to answer, but certainly some of the concepts and the framework we develop can be used to answer or to that research question as well. But thanks for the question.
Okay, thanks. Do you have further question, Corina? Do you want to give more precisions or?
Thank you. Thank you. It's very interesting. Thank you.
Then I have two other questions, one from Irene Merck, another from George John. Perhaps first Irene Merck, who just shared a remark on the conversation. Maybe Irene, I let you just explain and maybe explain the graph you shared on the conversation, and then Anne and Anastasios will react if you agree.
Yes, thank you very much. I acknowledge it's a very small print graph and without too much explanation.
Yeah. You can share them, I don't know, maybe.
I can definitely share after the call. I think it came to my mind when Han was talking about the challenges, and one of the challenges is that it's, and I found that personally very interesting when we did the SCOR internal work on that you can already see that in regions of the world, or in regions of the US specifically, that are accustomed to higher temperatures, there's a lower extra mortality compared to regions that are not accustomed. That's exactly what you were saying right now, Anastasios. And these pictures that are shared is basically increased mortality as a function of extra temperature. So for somebody who's used to an average temperature of, in Celsius 25, 35 is hot. But in some regions of India, 35 is normal and 45 is hot. So it's not the absolute temperature, but the relative temperature. I always use this illustration when we go to the south of Spain for holiday. We only put on a T-shirt and flip-flops, so we cannot imagine to work. Whereas people around us, the gardeners and the cooks and so on, work 8 days, work 8 hours, and are used to these temperatures. And I think it's very, very well related to what you have been presenting, and I really like the fact that this is a link together. Yeah.
Thank you, Irene.
Irene, could I just ask if that
Yes.
graph that you shared is that from a source that you can share, or is that your own analysis?
It's actually something we use in our internal work because we did also some quantifications, and it's not proprietary. I'm absolutely happy to share that. And it also, in addition, the different colors show different years, so you can see that people become more resilient over the last decade. So I'm definitely going to share that with you. Yeah.
Thank you very
Thank
much,
you.
Irene. Yeah.
Okay. George John, Professor John.
Yes, thank you. When I look at your main graph, I see a link between temperature and mortality, but I don't see climate change on that graph. So could you have two graphs, one when climate change was very low and one when climate change? And this is the first question. The second is, could you conclude on any causality link between climate change and mortality with your analysis?
Okay, so if I can respond to the first question. So one of the challenges here is the data availability. So we're looking at for the mortality data, although the data goes quite far back at a high level of aggregation, at the level of aggregation the level of spatial resolution we're looking at, the data is only available for about 20 years. Now, of course, climate change has accelerated a lot in the last 20 years, but obviously this is a longer term picture. What I would say, and something that we are looking into, is the idea that there are various scenario-based projections of climate change, and in some of these cases, in fact, they say what is going to happen to temperatures at a climate division level. What you could do potentially is feed that through into our model, and then that would tell you the business as usual level of deaths, and then the level of deaths under different climate scenarios. Because I think it's important to recognize that we still don't know to what extent we will mitigate the effects of climate change, to what extent things might get worse. That depends on many factors that are, I mean, I do forecasting, but these things are very difficult to forecast. So I think instead we can look at various scenarios and look at projection-based forecasts and say, under this scenario, this is where there will be more deaths, this is who will be dying, and that's really the benefit of this model.
Okay, and for causality?
I would be very, again, as a statistician, the first thing you teach students is that causation and correlation are not the same. These are regression models. So I would be, so this is why we take so much care to control for as many confounding factors as possible. Yeah. So insofar as we've got the right confounders in there, you could say this is causal. But of course, there's some unobservable things that, of course, you could come up with, and that would perturb our results somewhat.
Yeah. The only thing I would say, like, to make the like the causal link more real, like if such data becomes available, if we have on top of like this fine regional level, a different age group at different months, if we have cause of death data available, like this would be better, like because we know certain cause of death are more likely to be associated with extreme temperatures, etc. If we can pin that down, the relationship could be more convincing. But currently, as we've talked about in the presentation already, we have quite a big data suppression issue for certain regions. So at the moment, like it's simply a limitation of the data that we face. Yeah.
Thank you very much.
Thank you for the question.
Yes, please. There are probably other questions. Don't hesitate. Yes, I see that Kwame Bandele. Perhaps Kwame, you could explain your comment and your question, if there is.
Sure.
Thank you.
Yeah, it was. I did a study to try to explain why the mortality from a heat wave in Chicago was higher in Chicago than in St. Louis, even though St. Louis had higher temperatures. Now, part of that is explained by what one of you just said, that St. Louis people were accustomed to higher temperatures. But I looked at the data and I found out a stronger relationship between the nighttime temperatures and the mortality. So at that particular time, cause of death was not precisely captured. They might have something like respiratory distress. So we just looked at the pure mortality rate. But the nighttime temperatures in Chicago were relatively higher than the nighttime temperatures in St. Louis. And it ended up explaining the outcome a lot better. So I just thought when we're throwing together graphs, I remember usually data is available for the daytime high, but actually the nighttime temperature can be more useful. That's all.
Do you want to go first?
You can
actually,
go first
I'll
on
go
this one.
first. Yeah.
Okay.
So yes, thank you very much for the question, and I absolutely agree with you. So, like, in terms of the temperature data, like, probably I explained. I can't remember exactly where I explained we're using the average temperature. So that means, I mean, some people were using like a maximum temperature of the day or minimum temperature of the day, and we actually experimented this as well, and found out that the average temperature is better because it's not only a snapshot of the hottest or the coldest time of the day or the months, it's like an aggregation, or it's like an average throughout certain time periods. But I absolutely agree with you. The distribution or the pattern of like the temperature is actually also playing an important role. And in a heat wave, like during nighttime, if the temperature is not going to cool down, like it will have bigger impact on population health comparing to, like it's really hot during the day, but at nighttime it kind of cool down so people can sleep well, etc. So I absolutely agree with you. Currently, we don't have information at climate division level for the nighttime temperature from NOAA, but if such data is available, I would agree with you that like nighttime temperature should be considered. And the other thing I want to mention is what we're looking at, this average temperature maximum and minimum. None of these measures are like perfect. So basically, if like for future study, if we want to quantify the impact, it's better to kind of do our own indexation for this particular problem. But I absolutely agree with you.
The thing I would add to that is, and thank you for comment for that. Like that's an excellent suggestion. One of the challenges with that is that we do have to look at monthly data, because some of these climate divisions that we're looking at are very sparsely populated, and otherwise you just have too much data suppression. So it's one thing to look at Chicago and St. Louis, which are big cities, but then if you're looking at some climate division somewhere in rural Idaho, then You just will not get data at such a fine temporal resolution. So there are these trade-offs, but certainly we want to put more thought into the summary of temperature that we use. We do need to summarize it to match it up to the death data, but I think we can do better than average temperature there.
Yes.
Whether that's max temperature or the length of heat waves, and it would be, yeah, we should look into the NOAA to see if we can get something on nighttime temperatures, because that makes a lot of sense.
Yep, I used a source called Weather Underground, and it was difficult manually to pull together those nighttime. It's not widely available, but thank you.
Yeah, right. You're right. Yeah.
Yeah. Okay. Yeah. Thank you.
We have a further question from Iran, who asks if you are considering splitting further the results, for example, by ethnicity, but maybe we could add other consideration, social status, etc., etc. There are different dimensions of heterogeneity of the population, not only age, but of course gender and different other dimensions. Is it something which you have sufficient data to consider them? Have you already observed something? Okay, I let you just comment on that point.
So we can look at the data broken down by ethnicity. Han would know better than me, but I don't think we can break it down by the socioeconomic status at an individual level. Like
no,
right?
we don't have individual level data for that.
The challenge is that the more that you break down the population, the more you run into this data suppression issue.
Yes, sure.
So this again, this trade-off keeps, because we did think about this, but this trade-off keeps coming back at you. So particularly, again, we're looking at the whole country, and while some ethnic minorities might be 10 or 20% of the population of the US overall, there are some of these areas where there's very few African Americans or very few Latinos. So this is again, this is the challenge. You just run into this data suppression issue, and there's just no data. It's just all suppressed.
Yes,
yeah.
and probably if we look, for example, by ethnicity, you should cross-look also with social status, because it's maybe the social status and the fact that you don't have sufficient equipment at home that may explain why you are more exposed, etc. And therefore, of course, in order to be sure, not only perhaps not causality, but of course we don't enter in there, and therefore someone of course asked by education level.
So again, I think with all of these questions, the best that we can do is that we are getting these results out for different climate divisions, and we know something about the socioeconomic composition of those divisions. Now, we have to be very careful here, because it might be the case that there is a region that is poorer or has a larger number of African Americans, or has a larger number of highly educated people. And if whatever we observe there, we can't attribute it necessarily to those factors, because this is the classic kind of statistical problem of a composition fallacy. But it's at least indicative of something in that direction.
Yeah, I was gonna say we do have this climate division, like random effects. So like in a sense, like we don't have. I mean, first of all, we really don't have individual level data for the education level for on the death certificate. We don't have such information, right? But on the other hand, we do have this climate division, random effects, and that's indicative, as Anastasia just mentioned, like the climate division level is already quite a fine geographical resolution. So we could know something about certain climate divisions. So what's the average like education level, or what's the percentage of high school completion for the population there? What's the, like the population structure in terms of ethnicity, etc. We may be able to draw some conclusion based on the like regional level statistics, but just not at the micro level or individual level.
Just I am looking if there are other questions or remarks. Please, I see Zing Payet asking a question. Please, Zing.
So you are muted.
You are on mute, Zing.
Yeah. Hello. Thank you very much, both of you, for your insightful presentation. You speak about climate change on mortality results or effects. Have you looked into your studies about the longevity? Is something you considered or missing data? Maybe it's difficult to tackle these issues. Would like to get your thought about this, climate change on longevity, effect. Thank you.
Thank you, Zeying. So in terms of the impact of climate change on longevity, because we are like modeling this relationship, we are modeling the relationship between like extreme temperature and the mortality experience. And as Anastasios mentioned, we can run these different scenarios. We can feed different climate scenarios into our model, and then we have a bunch of like a forecast or predictions for the mortality, for different mortality scenarios based on the climate scenarios. And then we can compute what will be the longevity impact, because longevity is like we can calculate the life expectancy of a certain population for the next couple of years. But what we can do is a scenario-based projection. So we project the longevity level given certain climate or certain temperature scenarios, and we can see the difference between we can see how big the difference is across different scenarios, and that gives you an idea of how much impact extreme temperatures or like other climate change factors have on longevity. Yeah. So Tas, do you want to add anything?
Yeah, no, just that there's generally a flow on from the results on mortality through to longevity. So we will have some conclusions to make about that as well.
Yeah. Thanks for the suggestion.
Thank you.
Are there other questions? Please don't hesitate to raise your hand, or if they are not, I have just a small question, which is, of course, crossing many other questions. When looking at your slide 43 and the graph which is presented on slide 43, what is impressive is that we see the rate of mortality increasing at relatively low level of temperature. View from my point of view, 80 degrees Fahrenheit and 90 degrees Fahrenheit is something we all know, even in Europe during the summer period. And then my question, because from this point on, we are entering an area where the increase in temperature may be long-lasting. If it is below 30, for example, in Europe, 30 degrees Celsius or 90 degrees Fahrenheit. And of course, if we continue to increase, we will be confronted with shorter and shorter period of heat. And therefore, do you think that you could be able to have this double weight of the level of the temperature and the length of the head period, because here you mentioned it at the beginning, but it's relatively important, in fact, in order to see what is the risk.
So the first comment I would make is that it does seem low that in the mid-80s you're getting this increase in mortality due to heat, but these are monthly averages. So it is possible that for a lot of these cases where it's a monthly average of 90, that there was a heat wave of 5 or 6 days over 100. So again, this we've touched on this before. We've talked about nighttime temperatures, using the max, using the min. And something that I think will be a very useful predictor to use will be the length of a heat wave within a month. This just makes so much sense. So again, this is kind of on the list of things to try in that regression function. But certainly I think that's going to be very relevant.
Yeah, I agree. Thanks for the suggestion, Philip. And I've seen some existing research in climate science. They have this like indicator, like a dummy variable. If a heat wave happened in the time period, they have a dummy variable capturing that. So I mean, it might not be the best way to capture this long-lasting extreme temperatures, but like certainly that's a direction that we can go further this project.
It may solve some problem of data. If you don't have sufficient data, of course, it may help just smoothing the problem. Okay. Do you want Han and Anastasios add something, add some comment, or?
Well, again, we would just like to thank an excellent audience. So many interesting questions and excellent feedback for us to continue to think about the research. And of course, Han already thanked the SCOR Foundation for the support, but I'll do the same now. So
and on our side, we are thanking you because you gave us an insightful presentation, which is raising, of course, new questions, but at the same time providing some first answer, which are very important. And it's really very stimulating webinar. And in the name of all participants, I would like to thank you so much. And of course, thanks all those who have been asking questions and or making comments and participating to this webinar.
Philippe, maybe just a point, because some participants wanted to have the presentation. So just for your information, as you are invited to this webinar, and you can get the link to the replay, replay of the record, in which you will find how to the presentation of Han and Anastasios.
Yes, it's on our website. Therefore, with the agreement of Han and Anastasios, and of course, if you agree with Han and Anastasios, we put the link to the webinar in the website.
Of course, no problem.
No problem.
Thank you very much for your presentation.
Thank you so much. Bye-bye.
Bye-bye.
Bye.
Thank you.
Thank you. Bye.